There you go. Hello. Boom. Welcome to reading day.
That's C, Brett. Sorry. I don't take offense.
No. It doesn't mean I'm not sorry.
I understand. Just gonna pick on you. That's all.
It's the price check. All right. So material that we covered since exam 3. Maximum of Inertia, rigid body motion, Newton's second law from that. Rigid body motion, work energy, rigid body motion, impulse, momentum, and impacts. So those are the areas on the equation sheet that represent the stuff that we've done. And here's some like representative problems. Ooh, look at this. There are a couple more. I don't know where that problem came from, but yeah, we can do that problem. From spring of 2017, spring of 2014. Impulse and momentum, some more impulse and momentum, some work energy, some impulse momentum. So we got any requests? We're taking a request today. Freebird is the answer when someone says we're taking a request.
Go back to the circle.
Go back to the circle.
It's like one of the first questions.
Wait, so is it not cumulative? Or?
Well, it's kind of cumulative. I mean, to the extent that many of these things have.
It's not the circle one. Do this one. Not. Only this one. No.
You're talking about the circle one?
Yeah, this is not the circle one. But do
There's not many circles on this one.
Yeah,
The one with the drum rolling down.
that was the circle that I was talking about. But this is also
I think it's literally the next one. I'm sorry.
No?
Yeah, that was the circle one.
Because
Okay.
it has stuff from, like, are you saying because like these topics have stuff from
Can't let you do a circle.
everything?
So some of these topics end up, or some of these problems inevitably have something that's like related to, but it is cumulative in the sense that all of these things are related to each other.
Okay.
But I probably won't ask like a specific question that would look like, except for the fact that I should also include in here, and I've said this before, so I think I'm being consistent, that it's likely that you'll see a rigid body acceleration problem from exam 3. A problem like that, and then might ask for ICR, right? Just because it's something that's difficult and it is a measure of mastery of the topics. So, but I also just, I'm providing problems that I've done before, or have been exam problems, so they're on exams before, from Coast Guard. We actually had 5 exams there for, including the final exam. Oh no, actually we might have 6, including the final exam. So we did a short one, a half an exam on vibrations. We had a lot of classes. We had more classes. There's almost 45 classes throughout the semester when you have 3 days a week. There's a lot more classes. Okay, so we have this winch. At A begins to pull up this 1,000 kilogram drawbridge starting at rest. The initial acceleration at point B is 1 meter per second squared upwards, or at least that's the vertical component of it, you should say. If the hinge is frictionless, use Newton's second law to determine the tension in the cable. Assume there is only one cable. And the vertical and horizontal forces on the pin. A properly labeled FBD and IBD is required as part of your answer. So let's switch over to Zakela. There's people from Must. And here she is. Right there. She knows. Just in case. All right, so not sure if all of this is. There's a lot of words up here. Blah, 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 blah. Anybody ever read all that? When you have too many words, nobody reads it. So that's what I am with greeting cards. If somebody has too many words. Just don't read it. so, we could start off, we got a couple choices, because this is pinned right here. So I might go for the maximum of inertia about O, which would be different, I didn't bring my calculator, would be different from what the posted solution is gonna be. But it's one of our choices is, so I would take the maximum of inertia about O by taking the maximum of inertia of the whole thing and then moving it the distance from the center of mass here to O, right? So I might go R center of mass to O squared. Could write that a bunch of different ways. And if we have equation sheets, which if you don't happen to have one with you and you want one, I think I have a few. Not a bad idea to grab. All right, so here we can, I'm gonna go ahead and use a long slender bar. It looks slender enough to me, but if you want to use a flat plate, you could, but if you're around this axis right here, you end up getting the same 112 mb squared versus 112 ml squared. They all end up the same thing right there. So 112 ml squared plus m, and now this distance, well, let's just keep it this way for 112, and there's these, yeah, it's nice that we have this in SI units, and so we have the total length is 7 meters, and we're going to take 1,000, and now this distance, we have to do a little bit of thinking here. So we have a 3.5 minus 2, right? So that would be 1.5 that we're going to move the thing? Yeah, sure. So I'll take 49 divided by 12, and I can add it to 1.5 squared. Take a shortcut, multiply by 1,000, and get 6,333 kilogram meters squared. And now I'll do my FBD and IBD. And let's see the forces acting on this. We're going to have the pin forces. So I'll go Roy, and then rocks. Force due to the tension. We'll have the weight of this. I forget anybody? I don't know. It's at 30 degrees, but. And then on here, I guess I'll go ahead and do this right here. We're going to have the mass times acceleration, m, a, I guess it'll be the center of mass. We're also going to have the I of O times alpha. So if I take the sum of the moments about O, in this case I can write this thing out because it's a pinned problem. I can write that. I would otherwise write the effective moments, but because it's a pinned, it's a special case where we can write that. And I'm going to declare counterclockwise as positive. So I'm going to get the tension in the cable, but it's only going to be the perpendicular portion right there. So it'll be Ft, it'll be negative because it's going clockwise. Which I could have probably saved myself some time by making it the other direction, making it clockwise positive, that's right. So now it's going to be the sine of 30 degrees. But we also need the moment arm. I'm just going to go ahead and put numbers in there. So I'm going to put 5. right, that distance right there. And, let's see, we're gonna go plus mg, so 1,000 times 9.81. Don't forget, we also need the moment arm, which is 1.5. And then it's gonna be equal, and we've drawn it clockwise, well, we know it's gonna be clockwise, so it's still negative. And that's our 6,333. And, it's gonna be times alpha, right? No, we were told something already. Oh, we needed to do a little, a detour into kinematics, my apologies. Not too much of one, but in terms of the paper left, let's see. Let's just do a little departure here. So we'll call that equation 1. We have the kinematics. It won't kill us. Well, this is pinched, so we're fine right there. We don't have to do a 3-diagram method thing here. We're moving about here. But we know that this right here is the acceleration at b, and we know that the acceleration of b is going to be equal to, well, I'll just put on 5 times alpha, is that distance right there, which we know we were told is 1 meter per second. So alpha is 0.5 or 0.2, right? No, right? Yes, 0.2.
Are we looking for the velocity?
We were given the acceleration, right here.
What's the next one? I think it's, what's that here? I was thinking it's velocity.
So it's going to be radians per second squared. While we're here, we might want to get the acceleration of the center of mass, which is just 1.5 times the alpha, or 0.2. So that's a useful thing for us to get 0.3. Okay. Yeah, 1.5 times 0.2. Yeah, 0.3. 0.3 meters per second squared. Good news. Now we go back up to 1 here and find what the tension is going to be. So that should be, let's see, this comes back over here to add with this, and this goes over there. All right, so we're good with that. So we have the 6,333 times 0.2, and we're going to add to it the 1,000 times 9.81 times 1.5, and we'll add those together, and then divide by 5 and divide by the sine of 30, boom, and we should get 6,393 newtons. And then, so that's part A. And then using the sum of the forces in the y direction equals mass times acceleration in the y direction. We should get Ft, or 6,393 times the sine of 30 minus 1,000 times 9.81 plus Roy, and that should equal mass times acceleration at the center, so 1,000, and the acceleration was 0.3. So violating our margins right here, which just seems wrong to me. take the 300 and add to it 9,810, boom, and then subtract out the sine of 30 should be 0.5, boom, so we subtract out of it, so we get 6,914 newtons, and that's going to be positive, so we went upwards was correct. And then the sum of the forces in the x direction, you say mass times acceleration x direction, but there is no acceleration in the x direction. There would be if this thing was moving, already had an angular velocity, right? Because then it would have, don't forget centrifugal acceleration, it's easy to forget it. But because it has just started to move, it doesn't have any normal acceleration there. So that's actually 0. So it's just going to be 6,393 times the cosine of 30 plus Roy. And there's nothing else in the x direction. All this stuff is on the left-hand side. It's that guy right there. So we end up with Roy is going to be 5,000, let's see now, I'll do the 6,006, 393, 30 cosine times, sure, 5,537 newtons, and it's going to the left. It would have been a negative number, we could see right here.
That's with the x direction, right?
ROS.
Yeah, you're right, yeah. I got so excited, I just turned my brain off.
You just like Roy.
I like Roy. More than rocks. I like rocks.
Change one of the equations. Please. Like the next to cosine.
Thank you. I should have left more paper here. Should have used less words, right? We already established those words are unnecessary because there's too many of them, so we won't be paying attention to them.
Less. Just less. Less worth.
Less is more? Is less more? Because I've often heard that more is more.
More is usually more, but less can be more.
Less can be more?
300s is more than 201s.
Tom Brady wins too many games.
We talked about that when we were in
Can we
here.
all-
I heard some of it. I heard some of it.
Tom Brady is the worst.
I dislike it.
Statistically, he's pretty good.
Statistically,
He wins too much. He wins too much.
Personally, I don't like it.
I liked him more when he was an underdog.
He just
And then
got
when he
retired.
became an overdog, didn't like him.
He just needs to retire. It's over.
Yeah. It's not apparently.
It just
It's
should.
not over
He's
apparently.
gonna-
Apparently
he's
he can do
gonna-
any damn thing he wants.
He's gonna figure out a way to go to the Super Bowl.
I did enjoy watching the Manning Bowl. I mean the Manning stuff.
They're always fun to watch.
That's the best way to watch football and the way I want to watch football all the time.
The Mannings talking over it.
Just the Manning stuff. Or just regular people talking over it
I like the
and,
tone-
and joking around.
The Tony Romo broadcast are always great.
He is better than no, I forgot his name. The other Dallas Cowboy announcer, Troy Aikman.
I like it.
I don't like Troy. Sorry, if this is being recorded and Troy happens to be watching Dynamics videos, I would hurt his feelings.
I don't think we're gonna hurt his feelings.
You don't think so? I think he could. Yeah, I think he's above it. Yeah. I agree with you. All right. So I want to say, see this one. This is you alluded to this. This is the circle one.
This is the circle.
This is the circle one. All right.
This
so
is what I was referring to the first time around.
I got you. I hear you. I will grade your last 3 homework assignments. I recognized that. I was looking at the other day, like, son of a. I thought, see, they were over to the side, and it only scrolled over so far. I was like, oh, good, look, I'm ahead. No, I'm not. All right, so you must use Newton's second law. Let's see, I didn't make this problem because mine would have been my graphic would have looked so much better. Sorry, Alicia. Methods to solve this problem for full credit. A 600-pound cylindrical drum with a 30-inch diameter rolls without slipping down a plane inclined at 25 degrees. So the without slipping is important. We want to determine the friction force of the plane on the drum and the acceleration of the center of mass. So first thing I'm going to do, I'm going to get the moment of inertia of the drum. Did they not give us, this is a cylindrical drum, right? So they didn't give us a radius of gyration. So we need to look this up. And it doesn't matter if it's a cylinder or a disc. Either way, we're going to have 1/2 mr squared. And we're using our favorite US units. Oh boy. So we need a 600 divided by 32.2. And the radius, this is the diameter, so we need 1/2 of it. And need to turn it into feet. So 600, 32.2 divided by 2. And then take 15 divided by 12 and square it. And I think I get 14.56 slug feet squared. Sure, somewhere. She always just leaves the things in there. It bothers me. Why? Where'd you put it in there? I think she's, she likes, because you can cancel the mass out. That's why she's doing that. All right. So you see the solution. You see Dr. Garcia's solution. Oh, I get it, the mass. I like the numbers. But it's interesting that, the things cancel out, but not that interesting. So, okay, I think we're ready for the FBD and IBD. It's 25 degrees. This looks like doesn't quite look like 25 degrees. So let's see. Something along those lines right there. So the weight's going to be acting downwards. So there's the weight. The normal force is going to be in this direction. The friction force now, you have to go to a question, which way is it going to go? Is it going to go up the hill or down the hill? What do you think?
Probably down.
The friction is going to go down.
Oh, you mean first is gonna go up?
So yeah, okay, so
I
it's
thought
going
you
to
were
be,
asking where the drums go.
I hear what you're saying. So there, I agree, the friction force will be that way. You could think of the friction force as the thing that's like making the drum rotate. Like if you were to think about if you took the moment about this spot right here, the normal force and the weight would have no influence on that drum. So it would have to be the friction force would have to be the thing that's making it rotate down that way. And so we're going to say that it can only accelerate as a translational down the slope that way. So we're going to have mass times acceleration there. And we know that it's rolling as well. So we're going to have I alpha about the center. So let's see, I didn't read remember the friction force on the plane, the acceleration of the center of mass. I think what I want to do here, right? So I'm also going to take an x prime that way and a y prime that way, and noticeably that's moving there, so we can make the weight only in here. So We don't need the normal force for anything, so there's no reason to do anything in the y prime direction. Make sure that you recognize that this right here is not true in this case because it's without slipping. This would only be true if it were slipping, right? So don't fall into that trap of turning your brain off and saying, hey, I recognize that variable and I recognize that variable. You know, one hint is that it didn't include the coefficient of friction. If they'd been just a little meaner, it would have included the coefficient of friction to try to trick you.
But then it wouldn't have said without slipping.
With that,
But then they wouldn't have said without slipping if there was coefficient of friction.
I agree with you, but like some people don't read, like me, like a lot of times. Like reading card, like there's too many words. I don't like reading.
That's
I'm an
more important.
engineer.
You should read that.
I'm an engineer. You should read the greeting card though. That's their frightening to do.
A little
But if one of those really long ones, like especially if there's if it rhymes, I'm not a fan of poetry. My daughter's trying to convince me. That I'm like, no,
You don't even like Edgar Allan Poe?
not so much.
I like a haiku, it's short and full.
I really hate haikus.
Haikus are kind of.
Haikus are nice.
I don't get them. I don't
They're
get them.
cool, but they're kind of dumb.
You're kind of dumb.
We're digressing, are we? You can see that one, doesn't it? Get to it. I'm not here for your haiku critiques. I got you. We can talk about this later. I'll have a long conversation about it.
How about
So anyway, if we take the moment about the center of gravity, which is, this is, by the way, this was in translation and rotation, so we can't do it about the pinned type of thing. So most of the time we would do like the, I'm tempted to say the sum of the moments about some point is equal to the sum of the effective moments, right? But if we do it about the center of gravity, we're always going to be okay right here. So we can take it about G is equal to I there alpha. So that's okay to say. So looking at this, and we're also going to take consider counterclockwise there. So we take this unknown friction force that we have right here, and it's going positively in a positive direction. And we'll take the radius of this, so that's going to be 30 divided by 2 divided by 12. And then there's nothing on the left-hand side here, because we're taking it about G, so that will works right through there. And so that's going to be equal to, and then this is going through the center, so in terms of the effective moments, it doesn't do anything. So what we're left with is I alpha, and we don't yet know alpha, so it's on 14.56 alpha. So we have to kind of put a pin in this one for the time being, because we don't know it. So they'll call that equation 1. Then we take the sum of the forces in the x prime direction is equal to mass times acceleration in the x prime direction. And the forces in the x direction, we'll call that positive coming up right here. We have this friction force, which we still don't know. Fn goes away, it's not there. But we do have a negative weight, and it's going to be the weight of this thing, which is 600 pounds, times the sine of 25 degrees. It's going to be equal to the mass of this.
But why isn't it cosine? What is the x direction?
Because we can see that it's the side opposite in the x prime direction. I got you. I hear you. We do it so often when it comes to the normal force, you kind of want to jump to the cosine.
Yeah, x cosine, y sine in my head. I always think about it otherwise.
No problem. All right, so we have mass times acceleration, and so the mass is 600 divided by 32.2, and the acceleration in the x direction, in the x prime direction, we can maybe write it over to the side here. kinematics. Maybe do I want to do this? I think I can go ahead and do it. Yeah, we can say that because we have this no slip condition right here, we can say that these two things are going to be related to each other. So we're going to say that the A right here at the acceleration g is going to be equal to alpha r. So I have alpha times 30 divided by 2 divided by 12. So that's going to be, maybe we could fix this up a little bit, and maybe I'll solve for alpha here. I'll put alpha over to the side, and take my 600 divided by 32.2, and multiply by 15 and divide by 12, and we're going to divide the f by this, so it's going to be 1 over. I'm not sure this is the best mathematically way to solve this, but I did it. So I started, so I'm just going to keep going. It's not probably the smartest thing to
Is
philosophy.
everything in terms of alpha? Then you plug
I'm just gonna plug it back into over here.
Okay.
Yeah, that's my. Maybe it made sense. Maybe to solve for f.
Should you just solve for something in the above equation and then plug into the second one?
Yeah, I'm gonna call this equation 2 in a second. I could have called this equation 2, except it had too much stuff in it. I figured I was gonna. I'm just rearranging this one to solve for that. So I'll take the 600, and that's just going to cancel each other out, isn't it? Yeah, I'll do that one. I'm painting myself into a hole here. I'll dig it out in a second. 600 divided 32.2 multiplied, and then take 15 and 12. So I think I did that right, but we'll see in a second. That's going to be 10.89. Yes. The 600 right there. That 600 would have canceled that part out right there. I think that's the correct value. I'll call it equation 2. So I'll just stick this back into there. So friction force, and remember that's 15 divided by 12. 1.25 is equal 14.56 times 0.04293 times my friction force minus 10.89. And oh, I bet this times that is going to be larger than that. That's what I bet it's going to happen. So we have 14.56 times. No. Why am I getting a negative number? That's fudge. Maybe I just, what did I do wrong? 14.56. I think everything up here is correct. That be negative? Maybe am I looking at this the wrong way? That should be negative, right? 600 is coming down that way. Oh, damn it! That right there is negative. Ah, thank you.
You You get like negative 21.7 for,
No, but, 1 second, this should be negative and that should be positive. Right, you see why that's negative? What was the mistake I made? It's going down the x prime, going down the negative x prime direction. So that should be negative. So when I rewrote all this out right there. So now these should add to each other. So that 1.25 and this right here, which came out to, when I multiply these two by each other, they came out to really close to 0.625. So I'm going to add 1.25 together. So just as an in-between step, I got 1.875 FF is equal to 14.56 times 10.89 times, yeah, I guess so. And then if I turn around, I get, yeah, I'm sorry, I forgot to write in this middle part, so forget that. Yeah, I get the right thing now. So I should get like 84.56 pounds, which is what, oh, I'm sorry, slide. And then, and then from this, we could go back, into, well, we could go to this equation, I guess, right here. Yeah, that's as easy as anything. To go, alpha is equal to, 0.04293 times our 84.56, plus 10.89, bless you. Thank you. 10.89, so we get, I hope that's right.
I got the same answers, but I did it differently.
Okay, good.
I got very close to the same answers.
It's easy to get a little
Wait,
slow.
my alpha actually didn't, but I got the 84.53 and my alpha was 7.257.
Yeah, you're right. You have the right answer. So let me see what I did wrong here. 0.04.
Friction's right.
293 times my 8. Oh, you know what? One was negative. That's why. I forgot mine was negative. So that should be negative, and then with the 10.89, then yeah. Negative. Should get 7.26 really radians per second squared. So the acceleration down the slope should be that 7.260 times our radius, which was 30 divided by 2 divided by 12. So 30, so just write 15. 15 times 12.
You gotta go down again.
9.75 feet per second squared. That's the circle one. Took me longer than it should. But wait. All right, so we did 2 Newton's second law ones. We would do either work energy or do a impulse momentum. Do the one from spring 14, impulse momentum. I don't like the way she writes things out sometimes. Sorry. So we're going to have a thin disk is moving to the right on a smooth horizontal plane, right? So this is flat. 3 meters to the second to the right, when it strikes at right angles, a slender bar pinned at the opposite end of mass 8 kilograms with a length of 30 centimeters. It has initial angular velocity. Ooh, it's going to, clockwise, interesting. So they magically hit each other at just the right position. I was almost thinking it would be swatting that way at it, but it's actually swatting this way. If the coefficient of restitution is 0.9, starts giving us directions here, but mostly on the diagrams. Show the normal and tangential components, determine the magnitude of the tangential velocity of the disk and the bar after the collision, determine the magnitude and direction of the velocity of the disk immediately after the impact, and then determine the magnitude and direction of the angular velocity of the bar immediately after impact. So, what is she saying here? Determine the magnitude of the tangential. That right there is a trick problem. They're 0, because the tangential direction is that way. And there wasn't any tangential before, so there isn't going to be any tangential after. Tricky. As with anything, I'm going to give the maximum of inertia of the bar, get that out of the way. And I'm going to do it about O. Makes life just a little easier. So I plus M, and then this is going to be L over 2 squared. And that bar, once again, is 1/12. So 1/12 mass of the bar. A slender bar pinned at the opposite end is 0.8 kilograms. And the length is 30 centimeters. 30 centimeters. Centimeters bother the hell out of me. I can get my head around millimeters, but the centimeters. Right? So that 30 centimeters is 0.3 meters. I guess it doesn't bother me now as much as it's. So there's a little mental gap when it comes to. Yeah, 0.3 divided by 2. So this is about the center of the mass right here, and we're moving it half the length, so it's right there. So 0.3 squared times 12 divided, right? And then 0.15 squared times 0.8, add them together. So I get that this is 0.02400 kilogram meters squared. That's just little initial stuff. We're going to want to know the velocity, the initial velocity of a point that we will label. Let's just, even though this whole thing is called B, let's name that point B. That's the point of where the collision right there. So we'll find the velocity of B1, I'll call it, is going to be, and we're assuming that it's right there at the tip, even though there's a little spot right there. I always dislike that part, but we're going to take omega 1 and do L times it. So that's going to be 2 radians per second times 0.3, and I can do this, is going to be, ooh, what happened there? Ooh, I see what I did. She's got so much stuff written on this page, it's hard to follow it. I'm just going to believe in myself. It's going to be 0.6 meters per second. Right? I'm going to need that in a little bit. So we will write out now the 3 diagrams here. Initial, impulse, and final. They're kind of putting close to each other, didn't I? I don't really need the impulse. gonna draw them a little bit separate from each other, even though they're not. Oops. And so here we go. We have our MAVA1 IO omega 1. We're gonna have these crash, kaboom. Also have these going on right there. But they're gonna cancel each other out. Also, we could write out these right here in R's. There's nothing in the y direction, so there really wouldn't be any right there. And, but there would be here in the x. There could potentially be some in the x. So that's the reason why we're going to take the angular momentum about this and about that point to avoid this. So after this, I'm going to go ahead and assume that it's going to continue in this direction. So we'll get the I omega 2, and then this is going to be MAVA2. So sum of the H about O1 plus the sum of the moments about O dt, say my office hours, equals sum of the moments about O of the angular momentum in the second case. So almost everybody's going to be negative here, but we'll keep up with it. So it's going to be negative MAVA1, but now times the length of the thing. And negative IO omega 1. And then everybody here cancels out. So it's going to be equal to, and we're going to assume that it keeps on going, so we're going to go negative MAVA2 times L, and then minus IO omega 2. So we put in a lot of numbers here. 1.5 is this mass. Initial, we actually even included the radius. It doesn't need we don't think we need the radius for anything. Jeez. Hope not. I don't think so. Velocity of this, vertical velocity, 3 meters per second. And the length is 0.3. I is, hopefully, did that right, 0.24. Omega 1, we're saying is 2 radians per second. Here's where we start getting unknowns. Minus 1.5, don't know this, times 0.3, minus 0.0240, and then omega 2. So a bunch of junk. Chickaboom, chickaboom. All right. I see what you did there. All right, 1.5, 3 times 0.3 times, so it's 1.35, and then 0.024 times 2, add them together, so we have 1.398. 1.5 times 0.3, should be able to do that in my head, but I didn't. So you get negative 0.45 VA2, and then minus, I'll just leave this one, 2400, omega 2. Call that equation 1 with the 2 unknowns. Now, go to the coefficient of restitution. Oh, wait, that should have been negative right here. So we could have got rid of all those negative signs. made our lives just a little easier. I forgot about those negatives. So we go to coefficient of restitution. And so we're gonna say that that's gonna, E is equal to, I guess I'll go VB2 minus VA2 divided by VA1 minus VB1. I think I did that right. So, I'll take that 0.9, coefficient of restitution, I'll multiply it by this bottom part here. VA1 is 3, right? Minus VB1, and this to the right, so it's positive, right? So we're going to keep that right. And then we established this is 0.6. And then we don't know either one of these. So 3 minus 0.6 times 0.9, we have 2.16 is equal to VB2 minus VA2. So that is equation 2 for us. And lastly, so we have 3 unknowns. We have A2, omega 2, and VB2. But we know that omega 2 and VB2 are related to each other just like we did up above. That VB2 is equal to omega 2 times L. Therefore, it's 0.3. So we can stick that back into here. So 2.16 is equal to 0.3 omega 2 minus VA2. So we've just now, I could have called that equation, I could have called this equation 3 maybe. Now this is equation 4. We can stop numbering equations now. Now we just combine this equation with this one up above. Maybe, I guess because I have A2 isolated already, I'll move this guy, actually I bring him, yeah, I don't like algebra. I'll substitute into there and solve for that. So I got 1.398 is equal to 0.45 times, and I guess that's going to make this 0.3 omega 2 minus 2.160 plus 0.20240 omega 2. And now I can solve for omega 2. Even though I don't want to. So let's see, 1.398, and I have 0.45 times my 2.160, and that's going to add onto there, boom. And then I'm going to have 0.45 times 0.3, and that's going to add to my 0.024. And then I can divide, and hopefully I get a 14.91 radians per second, and that, according to this, is the correct answer. So that's actually, and this was, as predicted, it was going to be clockwise, so therefore it is clockwise. Don't rely on the signs here. We made a prediction, and it came out positive, therefore our prediction is correct. And then the other part of it is we want to find out, we could do it from either one. I guess I'll do it from what I'm calling equation 4, might be the most straightforward one, where I say VA2 is going to be equal to the 0.3 times my 14.91 and minus 2.160. 0.30 times, and then 2.16 minus, and I get 2.312 meters per second, and it's going to the right. Algebra was annoying there. But you see the solution posted, you can see her approach onto the thing. I'm not saying mine is any better, but at least for my comfort level, I found that I could, that's how I would approach it. We have we're taking requests. No free beer though. No Mustang salad either. Won't play Mustang salad. Just won't play. Play that funky music, white boy. Just will not play. Won't play. Won't do it. I will survive. Never playing that song ever again. Yeah, you don't even know the song.
I know the song.
You know the song?
Why won't you play it again?
I just played it too many times.
Just do it.
I don't even. It's even started to get in my head. Get out of my head. Don't want to hear it.
What about RESPs?
No one's ever asked for that song. Not to me. No. We did have a female singer at one point. I say we, a band I was in had. So, what's interesting enough, by the way, Aretha Franklin didn't write that song. Not even the first one. That is a Marvin Gaye song. Is it a Marvin Gaye song? It's a Marvin
I
Gaye
think
song.
it actually goes. Where you
Really?
I thought Marvin Gaye was the right answer.
Oh, this is one that I wrote that's too complicated.
Yeah, I don't want to do that. That looks,
Okay, cool.
no,
You don't like that one?
I don't like
Alright,
that.
well, look at that. He's like,
maybe an ICR one.
Yeah, I like ice. I don't like
oh,
ice.
I see. I don't know. Oh, boy.
This one also looks hard.
We might have to invent one.
Inventing a problem will work.
Invent problem. Don't know. We just pick one out of the book.
You're gonna have the monkey scale the Empire State Building at 133 miles an hour.
Yeah, it's dangerous thing to do. Don't wanna. We could start causing all kinds of problems with large monkeys climbing buildings.
Oh, you're really gonna create a problem.
Really good at creating problems. That was actually, I think, on my second grade report card. Really great at creating problems.
Oh.
I was uniformly despised by a number of my teachers.
I've never had a teacher talk about how bad of a student they were so much. You always say how like you were such a bad student. I don't believe you. You're a teacher now.
I have my grade cards. Not to go dark, but my mother passed away several years ago. My little brother and I were going through the stuff, but she kept my grade cards. I'm like, I was a terrible kid.
It's probably for a good laugh every now and then.
Oh yeah, they're good. I tried to inspire my son by showing how poorly I did at one point, and saying,
Did it backfire?
yeah, totally.
He's like, if you did that, why can't I do that?
Yeah, exactly. Okay, so some of these, look at this one right here. I'm trying to figure out where the ICR is. I think maybe it might be in, no, okay, we can do this one, right?
Sure, I have no idea how to do that.
Do the ICR of this one, can we,
Is that why is it cheap story?
this guy right here?
Yeah.
Well, I don't know. I think it's actually going to be a strange spot here because it's going to be the intersection of these two things. So I think the ICR is actually right there.
How about we do the next problem so it's not so.
You do this one?
Yeah, is that better?
This one's very similar to one we've done before, but that's okay. We can do that.
Sure. I don't remember doing it long.
And maybe we should find what the acceleration is of the thing too. So 134. The acceleration can be quite hard, right, to find the accelerations of some of these.
Sure.
Onto this. They're giving me the acceleration, but I thought this was in the section that was whatever. Okay, so let's fresh piece of paper. Good place to start. They don't give us the angle, which is not as annoying to me. What they give us, and it's in millimeters, better than centimeter. Very stout count. 100 millimeters. This is 175. $200. Now this is given as 75 millimeters. Here. So, and this is E, D, spells Ed, double A. So other things that you might want to find here right away is I'm going to go LDE. I'll call this theta E, and sure. So LDE is the square root of 75 squared plus 275 squared. Sure it is. 75 squared or 275 squared. Here we go. Plus squared. 285 millimeters. And then theta E inverse tan. 75 over 275. 15.26. And information they provided, they say that the instance shown AB has an angular velocity of 10 radians per second and angular acceleration both clockwise. So that would be this way right there. So the alpha AB, well, I did the alpha first for some reason. The omega first is the 10 radians per second. This is the 4 radians per second squared. So the angular velocity is usually a pretty easy one. It's just the ICR. The best way, I think, to approach it when you see a 4 bar is to just extend the lines. If you just extend the legs, of course you can't quite, this one runs off the page. You can see what these are going to be, so maybe we draw like a little bit of a smaller version of this thing. So that we get kind of a sense of what's happening. So start out finding the velocity of B is simply going to be omega AB times the length AB. So 10 times 175. I'll keep everything in millimeters because why not?
I'm so confused. Why'd you draw that thing on the side?
Because I'm going to want to get these distances soon.
Oh.
To do the ICR, because I couldn't get it. I couldn't do it over here because I ran off the page.
Yeah, I just didn't know why you needed the distances.
I was, I don't necessarily think in a linear fashion a lot of times, so I just jumped to something that I knew that I wanted to know. And then as soon as I got here, I recognized, oh, I actually need to do this first, or at least for my comfort level. Want to get this velocity out of the way. So 1,175 millimeters per second. So I know that velocity is gonna be up that direction right there.
Isn't it 1750?
Yeah.
Yeah. Randy will work. I don't know if actually I did meet that. Yeah, I kinda wanna do, the distance, I need this distance right there is what I'm gonna need here. So I did need this velocity, but I could see from my ICR that my angular velocity of this guy right here, what's called BD, is gonna be that direction. Right? So
Which is the ICR?
this is the ICR right here. And this right here is gonna be R, call it B with respect to ICR. And this distance is gonna be R D with respect to ICR. And we actually, this is, becomes a kind of an easier ICR problem because that is a right triangle right there. And then this angle is gonna be the same as this angle right here. So we can find that R B with respect to ICR is gonna be, this would be the rise, right? And this is the run. So we want to divide the rise by the tangent to get the run, is that correct? We okay with that? All right. Because I'm not, but all right. So I take the length of BD divided by the tangent of theta E, and I will get 200 divided by the tangent of 15.26. So I get 733.3 millimeters. So I can find the angular velocity of BD by taking BB and dividing it by RB with respect to ICR. So 1,750 divided by 733.3. Or 2.386 radians per second. And now we want to get the velocity at D. We can see that it's going to be that direction right here, VD, going in that direction. So we need the R, D with respect to ICR. So that's now, we're going to take, could do it a couple different ways, but we have the sign opposite right here. So we'll divide, this is the hypotenuse of that. So we'll take LBD and divide it by now the sine of theta E.
Is there a reason you're keeping everything in millimeters as we go?
I don't know, just didn't feel like the decimal places, but if it were a kinetics problem, we would not want to be in meters per second squared, and that kind of thing,
I'm
but
only asking because I was wondering if it affects the radian values.
it won't.
Because everything would be scaled.
Everything's scaled, yeah, everything's proportional. So we have 15.26 sine divided. That seems like close to the other one. I don't like how close that was. I guess it makes sense. Okay, 15.26. 759.9 millimeters. I thought these would be much different from each other, but I guess that's kind of a narrow thing, so the hypotenuse isn't too much far off. So the velocity at D is going to be that omega BD times the distance RD, let's rep to ICR, or 2.386 times 759.9.
Kind of an off-topic question here, but taking the square root and just using Pythagoras' theorem, I got 760.08, whereas you got 759.87. Which one is technically more accurate? Would it be just a rounding? I guess it's a rounding error.
It's probably a rounding error on the angle.
Yeah.
When taking the angles of the thing, that angle's small enough that it like matters. You could probably do something
Around here.
to give a there's probably some physical example we could come up with that you could see that just that slight variations in that angle result in a pretty substantial difference. So you can imagine then when rounding down to 3 sig figs, because I ran it at 4. I could have also plugged something wrong in, I don't know. So I get 1,813 millimeters per second. And I think the problem probably asked for the angular velocity of, this is actually an acceleration one. But before we do that, we would need the angular velocity of dE for ED. So omega dE is simply going to be the velocity of d divided by the length of dE, which we got, so 1,813 divided by 285.0. So I'm getting a 6.362 radians per second. And that's a prediction of that right there. We can continue with the acceleration portion of this, but I will say that, it becomes a little, I know that we've done an example that's similar to this at one point, maybe even a homework that was similar to this. It's a long problem, the acceleration one, but we could do it. It just becomes a...
Are you going to have it on the test?
I usually don't ask a 4-bar because it's just it's just a little bit longer than I think is reasonable.
So if you were to have a 4-bar, this is the extent of what...
Yeah, I don't ask about the velocity one's not so bad.
Would we still do another one where we have to find ICR to do this?
Sure.
Not necessarily the next question, but like a question.
Okay. I'm down with it. We should do a work energy at some point too. I can keep going with the acceleration of this. It just takes probably another.
If it's not going to go above 5, then it's okay. I think
Can you check the original problem for this one?
The original problem was problem 15,134, and I believe this is the 12th edition. If you wanted to see quickly. Wait 1 second. Paranoia will. So. Was that?
it's not wrong to think like that.
Yeah. I had my totally off topic. The drummer in my band last night, we had band practice, and his mother and father got scammed, got a phone scam. Really effective phone scam. They were able to stop the money. They were able to go to like the FedEx, one of the stations, they had the cops go to the FedEx station and stop the money that they had transferred, but they got this phone call that was supposedly from their grandson, my drummer's son, and saying, I just had a car accident. I borrowed a buddy's car down in New Jersey, and I drank a little bit of wine. I was driving his car, and we hit a pregnant woman, and I'm in jail, and here's my attorney. I hurt my mouth, that's why I sound weird, and here's my public defender, and they're saying, well, we need to send this money, and they totally,
The same thing happened to my grandparents. They thought it was me and they called me out there. I was like, I didn't get into a car accident.
It's, people suck. Well, some people
And I
do.
think my sister at the police station.
Then there's the real calls where you have the cops in and say, hey, we have your child. That's a fun
You
call.
had one of those?
No, not on the video. We're not having confession time here. 134, did I say 134? Yeah, so, and they did it by way of vectors, which can look a lot more compact, but let's see if we got I think we got the 2 point, this sounds familiar.
Yeah, you got that. You got 2.386.
Yeah, and then they started doing the acceleration analysis. So right here was them doing it with vector math and going through there. And then they go through the acceleration analysis.
That
Doesn't
seems like it'd be easier with vectors to get into acceleration.
it can be, I think so, yeah. It's the angles that make it difficult in the 3 diagram thing. But I think it also, this is just going through, your ability to make a force a math problem to work. All right, so let's proceed with another type of problem. We have a work it. We could look through the book for some, or we could go through some of the old exam stuff. Whatever floats your boat, as they say.
How many questions in the final 4?
It usually ends up being 4. Here's one we could do later on for an ICR and acceleration one.
Do work energy.
Okay.
Do one that you think is going to be similar to one.
Funny man.
Come on.
Isn't that how we all want it to be?
Yes.
I understand. I got the idea. So that's the reason why I give you ones that are like this, because I tend to have something not identical, but something somewhat similar.
Those look really confusing and hard. Why would you?
Everything looks confusing and hard
Not everything's an elevator.
when you first see it.
It's not true. That ball one doesn't look that bad.
This one?
Not the one before it. That one looks bad.
That one looks bad? But it's not really. I mean, let's see, it's work energy, right? So the elevator car E has a mass of 1,800 kilograms and a counterweight right here that's surprisingly larger compared to, I guess there's people have to fit in that, right? So 2,300 kilograms. If the motor turns, the driving sheave, so there's a motor up here, has a moment of 1,000 newtons per meter. See, I think this is an error right there. That's an error. That should be a Newton meter. If it's a torque, not Newton per meter. And that would be like a spring constant would be a Newton per meter. Determine the speed of the elevator when it has ascended 10 meters starting from rest. Each sheave, A and B, has a mass of 150 kilograms and a radius of gyration of 0.2 meters about its center of mass, about its center, pinned axis. Neglect to mask the cable and assume the cable does not slip on the sheaves. So, a number of things to look for here to start with, all right? So does it start from rest? If the motor turns, driving the sheave. when it has ascended 10 meters. So my first thought, all right, so the first thing that I thought about was I recognized that this is a work energy problem, right? Or we were told to do it as work energy. We could have done it in other ways, but I recognized we were told it was work energy, and then I saw that there was a moment and that this thing was translated. What do we know about when it goes to work energy, rigid body motion when it comes to a moment? That was the first thing that came to my mind.
Is this an external force?
Yeah, it's an external, yes, it's external being applied to it, so there's work being added to it. So what I want to find, when they told me that they translated this amount, I'm going to go, okay, how many radians then did it turn? Because of that external work that's being added. Does that make sense? How that's where my thought process like went to right away? Or could you have thought that? Like, would that be the thing that would trigger you to go, all right? Just remember that we're doing rigid bodies. That's the category of stuff we're working on, and we're talking work energy. And when it comes to work energy, that's one of the differences. And we had force times a distance for work before. Now we have moment times angular displacement. They're like, kind of, you can think of them as they are the same thing. Right, so maybe I want to go delta theta. Maybe is the first thing I want to say. How many radians does this guy turn around? I guess I'll go A right in there. What's going to be the distance divided by the radius? Right, so if he's moving 10 meters and his radius is 0.35, 10 divided by 0.35, we end up with 28.57 radians. We don't know how many revolutions that is, and we don't care. But we're going to want to multiply that by that moment right there, and that's the amount of external work that goes on. Other preliminary information. We were given the radius of gyration for both the sheaves, so let's find what they are. Remember that the radius, all we need is m. Sometimes we use k for that radius of gyration, but that's not a very good letter to use, especially when you're doing work energy, because we think of k being associated with spring constant. We could have just used r before, I don't know. They need to come up with more letters, right? We need to invent more letters, like use acrylic or something. I don't know. What do they use? Symbols. Coptic. What is it? What is the symbol? What is the Russian alphabet called? What are those letters called?
Why Russian alphabet?
I don't know.
Use that symbol.
I just was picking some. You can use Arabic. I don't care. I just want to try to. We need more characters. We don't have enough characters. Oh, they used K right there, see? It'd be confusing, it's unitly confusing. So 0.2 squared.
It's not so bad when there's not a spring in the problem, but when there's a spring in it.
Yeah.
Like there is one of the problems under the review that has a spring in it, so.
It's crazy. It's nuts. Okay. So when we go to do and then also, by the way, we want to start a datum somewhere. And it's unfortunate there's no pulley ratio right here, so we can say that the datum this is the lowest spot right here, right? So when this goes up, ascending 10 meters, this comes down 10 meters. So when we write out, and I forget which one I do first. Now that I'm at the end of the semester, my brain's like all in a fog. KE1 first. Is that what I've been doing usually?
Yeah. What do they call it in the book? V? T?
Excuse me?
Yeah, it's V.
In the book they call it T?
Yeah, you have capital V and capital T.
Yeah, V's kinetic, T's potential, right?
T is kinetic and
V
V.
is kinetic, V is potential.
Yeah.
It's not the letters.
There's other books that do that, and there's also some old books that do that. That's one of the reasons they didn't make that decision. But what can I say? I've seen other books that use this way, and I was just not enough letters. So the kinetic energy at the beginning, KE1, is equal to 0 because it starts from rest. PE1, I'm going to go ahead and choose that's going to be the counterweight right there. So it's mg, and we'll call it delta y. So it's m, I guess they call that c. There's a c right there. So the counterweight is 2,300, and gravity 9.81, and it's going to move 10 meters. 23. So it's a big number. 225,630 Newton meters. I just, as I'm coming through here. Yeah. The work that's being done between here is going to be the moment times delta theta, and the moment is 100, and we said that it was 28.57, and is that going to be 2,857?
Yeah.
Thank you, 2,857 Newton meters. And then the kinetic energy at state 2 is going to be made up of 4 parts.
4.
Fortunately, there's 2 of this. 2 of them are the same, with the angular velocity. So we're going to have 1/2 I omega squared. Well, it's going to be times 2, because there's 2 of them, plus 1/2 me ve2 squared, plus 1/2 mc vc2 squared. So I need to get rid of that. Well, I'll leave it. And by the way, we could also, while we're here, recognize that VE2 and VC2 are equal to each other, and also that omega is equal to either one, VE divided by that radius, 0.35. Excuse me, sir.
How did you get VE?
Excuse me?
How did you get VE? No, you like solved for VE under the bottom right of the diagram. So just
That's the answer.
That's the answer. I didn't do it. That was just written on there for, you're not the first person ever, you know. No, I'm just saying that this has happened before, that that people have gone like, where did that come from? I'm like, that's the answer, I'm sorry. I just happened to put it on there. I might not actually have done that. I could probably not take the blame for that. Nah, that's probably my fault, never mind. It never works well when you try to blame other people for things. I can still try.
I don't know. It's not your handwriting.
Not my handwriting. It's Sean Monis's fault. I miss Sean. And then here, let's see, ME is the elevator. The elevator tries to break us down. And 2,300. And I'm going to call that VE as well. We know that those are equal. So math. So 2,300, 1,800 plus 2 divided And we're gonna go, so this isn't actually a lot right here. Well, you are dividing it, right? So 0.35. Times 6. So this right here is only like 48.9 compared to this over here, which is like 2,000. So we don't get these wheels don't contribute nearly as much as the elevator and excuse me, I'm trying to say the elevator and the counterweight to try to stop. And then lastly, we have the potential energy because it's rising of the elevator afterwards. And so this 1800, 9.81, 10 meters. So 176,580 Newton meters. So now we can plug all those into this thing up above and say 0 plus 225,630 plus 2,857 is equal to 2099 VE2 squared plus 176,580. So 22560 minus 2857 plus, and then checking, divide, square root, and we get 4.973 meters per second. Yay, it's the same, it matches. See, not so bad after you do it.
Let's do another ICR order.
Alright, so I had picked out one somewhere.
Yeah.
Just put it somewhere out there. Searching randomly for it.
It's not last problem, it's gonna start reading. Spencer, just letting you know, it's gonna start raining in a few minutes. No. It's good, alright, it's just skateboarding.
Is it gonna make you sleepy? The rain?
No, it's just gonna get wet and he skateboards home.
Ah.
I can give you a ride as far as raining.
There's good sized stairs to go down on the skateboard.
Rain stairs?
No, they could be raining.
So we have this arm AB, beep, 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 has an angular velocity of 16 radians per second counterclockwise. At the instant shown, it's at 60 degrees. We're going to determine the acceleration of the collar and of the midpoint of this one right here, which just seems a little excessive, but that's okay. I mean, the reason why we would want to do it now, we recognize is that if we wanted to do the kinetics, that would be an important thing for us, but it just seems a little extra. First thing we need to do though is velocity analysis, so we're going to use ICR for that. And we can project the ICR rather quickly. Anybody want to hazard a guess of where it's located? Above, below, to the right, to the left?
It's gonna be below.
You just draw it from the pinpoint, you draw it straight out. And then from that, you draw it to the left. So the ICR is like, near like, kind of where 3.5 would where you just.
Okay, well, we,
Because the slider can only go left or right, so it's got to go on there.
Can it go
You have to remember the line that you want to do has to be perpendicular to the velocity. The velocity is going to be in this direction, right there, right? So the line that the ICR has to be, it has to be aligned with this. And the velocity here has to be in that direction. So the line perpendicular, so the ICR is up there. Does that make sense? Like here's the line of the velocity.
The line of velocity for A is,
You mean V?
for B, yeah, for point B, is the side of that line, yes.
Yep.
So then you can draw a line perpendicular from that, where that meets the line perpendicular to the other velocity, which is D's velocity, that's the ICR.
Yeah. So it's gonna be straight up like that right there. And then this one's gonna be in line. And they said it was going counterclockwise, right? So they were saying that right there, omega AB is going that way. So he's going to have a velocity that way right there. There's the velocity of B. So we're going to have a omega BD coming that way. And therefore, the velocity of this guy, which we don't really actually care about in this problem because they didn't ask for it. VD is right there. We have to get a little bit of geometry up here that they didn't give us. They gave us enough information, but it was just barely enough information. So would have been nice to know this angle right here, but they didn't bother to give it to us right in there. But we can find it. I might call that theta B, because it's the corner would be. And theta B, we'll say that it's going to be, we don't know this length, but we know the hypotenuse of this. So let's take the inverse sine, and so the rise of this, so we'll take the rise right here, opposite from this is going to be 120, and we're going to subtract out the 60 times the sine of 60, and then divide it by 200. Told you it would have been nice though. So that's 19.89 degrees. So that's that angle right here, so that's going to be the same angle as right there. And we need this RV with respect to ICR. I'm tempted to do it in a different way. But, well, we know that this angle right here has to be 30 degrees, right?
Yeah.
Because this one with horizontal is 60 degrees.
Is that relevant?
Well, I was about to say that we could get this angle by subtracting out that angle right there. This is the 19.89 degrees. And now we have that angle. And yeah, so This is gonna be 60 minus 19.89 degrees. So end up being 40.11 degrees. And if we know that, we can find this angle.
90 plus 19.9.
That's true, right? Yeah, you're right. We could also do that. 90 plus 19.89. And we need that for, was it 90? I don't need to do that, right? 19.89, I can do that in my head, right? I couldn't. So 109.9. Or 109.89. Then another sig fig won't hurt, especially when the first digit is 1. So we do the law of sines to find that. So we take RB with respect to ICR, and then the sine of 109.89 equals this length right here, given as 200, divided by the sine of 30. So RB with respect to ICR, take the sine of that, multiply it by 200, take the sine of 30, divide it, so we get 376.1 millimeters. And we hadn't got velocity of B yet, so like the velocity of B is the angular velocity of AB times the length of AB, which is 16 times 60. So 960 millimeters per second. So the angular velocity of BD is going to be equal to VB divided by RB with respect to ICR. Or 2.552 radians per second. Whoops. We don't need the velocity at D. It doesn't really help us anything with anything because this was about, this question is about the acceleration. We needed this because of the acceleration problem. Another piece of information we should get before we proceed to the main feature is we have this velocity of B. We also, even though this is rotating at a constant angular velocity, or at least we're assuming it did. I don't know if it said, yeah, no, it did say a constant angular velocity. We have to remember that we still have this acceleration at B is entirely the acceleration of B with respect to A in the normal direction, or omega AB squared times L AB. So 16 squared times 60. Which is 15,360 millimeters per second squared. So when we go to do the acceleration of this piece here, 60, so that right there is going to be 60 degrees. It's acceleration of B. This acceleration is going to be completely horizontal along that line. Doesn't look horizontal, but so go through our procedure here. We're going to take this and place it in both spots. And then pin it at the spot that's the reference. And we have two components to this. We have the normal component pointing in that direction, and then we have a tangential component, which we know is going to go along that line, but we're not quite sure whether it's up and to the left or down and to the right, but let's go ahead and assume, guess, an alpha BD in that direction, so that makes it that direction right here. So that's the acceleration of D with respect to B tangentially, and the acceleration of D with respect to B in the normal direction. And looking at our angles, here is what we had called theta B before. Right here's theta B. If you recall, our strategy most often is to first do the one that we know is going to be 0, right? So because the equation that we're writing out for this spot is the acceleration of D is equal to the acceleration of B as a vector, plus the acceleration of D with respect to B in the normal direction, plus acceleration of D with respect to B in the tangential direction. So we'll do the y direction first. Say 0 is equal to, call what we have. That is 60 degrees right here. So we have negative, I'll just put numbers in, 15,360 times the sine of 60. This guy right here, remember, we could put numbers in here, but I'll just go ahead right here. Is omega BD squared times L BD. You can see he's in the negative direction, so minus our 2.552 squared times that distance is 200. And remember though, it has to be a component, so we need to have the sine of that angle, which is 19.89. And then lastly, we're going to go plus alpha BD times its length, 200, and it's positive because it's going up. And now it's going to be times the cosine of 19.89. And we could already see from here that we made a good guess that it was going to be positive here because these are both negative. So we'll take the sine of 60, multiply by there, square times 200 times 19.89 sine times, add those two together, divide by 200, and then divide by the cosine of 19.89. And if I did this correctly, I get an alpha BD of 73.09 radians per second squared. That's counterclockwise.
And then when I do the X direction, I'm just gonna assume, keep treating it like it's positive, even if it's negative. It's gonna be negative, because that's going to the left, and that's going to the left, and that's going to the left. I'm confident it's gonna go to the left. So we go negative 15,360. Now this time it's gonna be the cosine of 60 degrees. Minus 2.552 squared 200 cosine of 19.89 degrees. And then plus 7, oh, not plus, minus. Oopsie daisies. 73.09 times 200, and now times the sine of that small angle, 13.89. So I wonder, why, oh why do I draw these borders around these pages if you can't fit everything inside? I don't know. Cosine times plus 15,360, 60 cosine times plus, I think it's negative 13,800, yeah, 13,878 millimeters per second squared. So that would be that way. Do I have the answer somewhere? I think I do. Oh, always a chance I messed it up somewhere. Always a chance. Yeah, I got the same thing. 13.88 meters per second squared. Thank goodness. How embarrassing if I would get the wrong thing. It's happened before. I am so tired. And yet, I have so much more work to do. I have to go to a meeting today.
Make the final.
I have to make the final. In fact, I have to make the final before I can go home. Today. After my meeting. Think I could bow out of the meeting?
Yeah, so you gotta make it done.
You know, if we need any help finding the answers of the final, I can double check.
Sometimes I Google them. Dynamics final exam. And I try to find other people's final exams.
Flip the page up.
So let's do that. Dynamics final exam, do the third link. We'll all study that one.
I gotta tell you, you won't be happy. I might be biased, but I think my problems are better.
My friend's Penn State dynamics course makes ours look like a different language. His is so easy. I help him with all of his work. It's a breeze.
There's other dynamics classes. There's lots of versions, lots of ways to skin a cat, but none of them are kind. You shouldn't go around skinning cats. It's wrong. It's just wrong.
Thank you, Doug.
You're welcome. I'll see you soon. When is our final?
Thursday.
2 days from now.
Yeah, 2 days from now.
You're tomorrow around 2:30.
Yeah, for not 2:30.
2:30,
yeah.
Kendra.